This is a sheet electrode which we used some longer time ago. It's not the best configuration in the world, and the cube is the one that I referred to earlier about when we made a switch from 250 milliamps per square centimeter after running for 9 or 10 months to 125. Something happened in the cell. A highly exothermic reaction occurred in the cell. We've also now noticed highly exothermic reactions on these electrodes, on 4.4 by 10 centimeter electrodes after running for some 800 hours. Again, we're seeing very large bursts of exothermic energy there. The curves were measured in the simplest possible way. The excess heat is measured fairly in this manner. We will notice that after we start our measurements at somewhere on a typical measurement, we would start at, say, 200 hours. We would then inject heat into the system by applying a known amount of energy into a resistive heater. We then let the system come to equilibrium. First of all, we top the cell up the night before, 12 hours before, so that the cell is totally filled with the D2O because it's been electrolyzed out, and the thing is left for 12 hours to equilibrate. Then first at 6 in the morning, typically we would start making measurements for 3 hours, and then temperature measurements for 3 hours every 10 minutes. And then then the heat would be applied. You wait till it comes to equilibrium again, and then you turn it off, and from that you can calculate the heat transfer coefficient. If you know what the amount of heat that you're putting in, you know the delta T that caused before it got back to equilibrium, and you can easily calculate the rate of the loss of heat to the surrounding solution. You then know the potential at this particular point. You know what the constant current is. You know what the temperature difference is between the cell and the water bath, so the excess temperature in this case would be 6.86 degrees, and from that then you calculate the excess heat. And that's demonstrated on this slide. This particular value is fairly new, and it's not in this table, in the table you saw just a moment ago, but this is just a typical calculation. So you know what the energy input into the resistive heater is. If you divide that by that delta T, that gives you the rate at which the heat is being dissipated to the solution. You know the heat output from the cell is also this cooling constant times the temperature difference, so you know what the output heat is. You calculate the joule heat, you know the cell voltage, the cell current, the thermoneutral potential for the reaction in the cell, and from that you can calculate the excess heating. We have also published a table of break-even, and this is based, when you want to talk about break-even, you of course have to take the various reactions in the cell into account. And in this particular case, we've considered 3 cases, and that is this reaction based on the joule heat supplied to the cell and this anode reaction. So that's what you see in the starred columns. The double star columns take the percent based on the total energy supplied to the cell, and the third one is the percent break-even based on an ideal reaction. Now this reaction may be this is a theoretical reaction, but it's a well-known reaction in electrochemistry, and that reaction is simply that you collect the gas, the deuterium gas that's boiling off of this electrode, pump it back around into a fuel cell anode so that you have oxidation of deuterium back to water on this side. So that the energy that it takes to do that, you're not really accomplishing any work here, so the energy it takes to do that at a conservative estimate would only be about a half a volt. So that's a very efficient process and requires very little energy to do. And the last couple of points I wanted to make, just one further thing about the actual pressures obtained in the machine. As most of you know, the confinement parameter, which is on the order of 10 to the 14th, 10 to the 13th, 10 to the 14th, I think a few parts 10 to the 14th to attain ignition in a plasma device, a high temperature plasma device. So we know what that is. We of course have extremely high temperatures in those reactions. In our case, we tried to form a simpler or a similar diagram, and we note from the lifetimes of the hydrogen in a palladium lattice and the density that we have in, we attain a very large confinement parameter or Lawson parameter on the order of 10 to the 36th. Even though we have our temperatures, of course, are a few orders of magnitude less than in the other experiments, it certainly means that we have a confinement parameter. So from the energy outputs that we get for the reaction we mentioned just a minute ago, these are the various rods we have used. These experiments now are essentially completed, and the open circles were experiments that were underway at the time. But these are operating in what we think is the break-even region for this given reaction. Of course, the other curve, this break-even line would shift up and down depending on which of the other reactions that you were attaining. But we were pretty sure that this is the reaction that's going on in the solution, at least at the electrode surface. This is the results for the sheet electrode, and this is the result for the cube that we had previously. Well, that's all the data I had. If you mind, could you put those overheads on? In closing, I would like to acknowledge Martin Fleischman, my associate in this project and graduate student who did most of the work in the recent months, Marvin Hawkins, Jerry Smith, who's in the audience, who's known about this experiment for some years and has always given us constant encouragement, Bob Hoffman for measuring the gamma ray spectra, Jim Brophy, Vice President of Research at the University, Ron Buller and David Williams from Harwell, who have assisted us with some experiments towards the end of the work. And the last slide is acknowledgement of support. Sorry about that, but most of this work, well, all the work initially was funded by ourselves for some time. More recently, the University of Utah and University of Southampton, and we thank Johnson and Matthey for supplying the rods recently or the rods for the experiments on their university loan program, and more recently for the Office of Naval Research for continuing support. Thank you very much again.
Are there questions?
Would you please comment on a report I heard this morning where you were talking with newsmen about duplication of the experiment with non-deuterated water, regular pure water?
Chevis Walling and Jack Simons have presented a very nice theoretical paper to a journal, which they expect to be accepted today or tomorrow, according to the reports. And in this theory, they very accurately predict the fusion rates, the energies that we should be seeing. And a couple of the other predictions they made is that we should see, one of them was that we should see helium-4. And then we never looked for helium-4, and we went back to the old mass spectral data for January, and sure enough, there's two very well-defined peaks at mass 4, one for the deuterium and one for helium-4. Which we've substantiated. We've gone back to the lab last Thursday and Friday and indeed have seen a large amount of helium, about 10 to the 4th times less than you would expect. I mean, 10 to the 4th times less than the D2 that's present, which is exactly the ratio that they predicted. A further thing they predicted was that the rate of reaction between deuterium or between between protons and deuterons is about almost 100,000 times faster than the deuteron-deuteron reaction in their scheme. They have a scheme of of shielding by a heavy electron of effective mass 10 times the normal electron in that lattice. And we had tried, did not do anything quantitative on it, but we did try in January to get a blank experiment with a palladium electrode that we knew worked in regular water, and we did not get heat in, heat out balance like we had expected. We did get some excess heat.